All right, so we have a few different conduction resistances. We have a convection resistance. We have a radiation resistance, at least an approximate one for a very simple situation. There's one more resistance that we should at least mention, and that's a contact resistance. So when you take two solid materials, and you smush them together, like I've shown here, this interface between them, it turns out, is never absolutely perfect, right? And there's some thermal resistance associated with that. So here I've shown two materials smushed together. I put a temperature difference across this whole big composite. So I have a high temperature on this surface and a low temperature on this surface. Material A has a high conductivity, which means that it's going to have a small temperature gradient, right? The heat transfer rate through this is the same everywhere. So therefore, I have to have a small gradient here in order to have the same heat transfer rate here, according to Fourier's law. So here I'm going to have a small gradient and then a large gradient. If there were no contact resistance, this is exactly what I would expect, right? And basically it's saying there's no resistance to getting the heat from material A into material B. That happens with no temperature change here at this interface. But if you zoom into that interface closely, you'll find that it's not perfectly flat. There's some roughness, and therefore, when you get close enough to that interface, the heat is actually going to have to constrict and go through some relatively small area interfaces, where some small area patches where these two interfaces touch each other, right? And that comes with a penalty, right? That constriction causes a thermal resistance. And so at the macroscopic level, if you sort of zoom out, what it looks like to us is that you have a temperature jump at that contact, right? So there's a temperature difference that's required right across this contact to drive the heat through these little touches where the asperities touch one another. There's another reason to have contact resistance, and that comes back to what we talked about last time, which is that in material A, you'll have some energy carriers. In material B, you'll have some different energy carriers. There is a penalty associated with getting the energy out of one set of energy carriers and into the other set of energy carriers, right? So even if you could make that interface perfectly flat, if the energy carriers aren't traveling from material A to material B, you're still going to get some kind of a contact resistance at that interface related to just the difficulty of getting the energy from one set of energy carriers to another, right? And that actually at cryogenic temperatures, that can be kind of a big deal. So this is our contact resistance. We usually characterize this penalty with a thermal contact resistance that we throw into our resistance networks. The contact resistance is usually calculated as an area-specific contact resistance, and that's some characteristic of how this contact is actually created, and then you'll divide that by the actual area of the contact, not the area of these little asperities, but the area of the whole thing, right? The area at large. So this is the area-specific contact. Again, this area-specific contact is not usually something you can theoretically calculate very easily. It's much more something that you'll find tabulated for you in different handbooks, and it'll be related to, what is the material here, what's the material here, what's the roughness of those surfaces, what's the pressure that you're pushing on these surfaces. Did you fill this gap here with something semi-conductive so that it's a little bit easier for the heat to get across it, right? So all those kind of empirical parameters will go into what's the actual contact resistance here. When you make these contacts, for example, at cryogenic temperatures, oftentimes you'll actually fill the gap with something like indium that's a very soft metal and can squeeze and take up some of these spaces to make it an easier transfer of energy across the gap. This is just a very abbreviated table showing some area-specific contact resistances for some interfaces, and you'll notice that it does depend on what are the materials, what are the clamping pressure, what's the roughness, what's in the middle between the materials. Is it vacuum? Is it air? Is it some kind of oil? And then over here you have area-specific contact resistance. The units of area-specific contact resistance must be Kelvin times meter squared per watt, right? Because then you're going to divide it by an area to get a resistance in Kelvin per watt, right? It makes sense if you think about it that the bigger that area gets, the smaller that contact resistance will get. So you divide by that area, you don't multiply by it. All right, so this is then our list of thermal resistances. This is kind of our arsenal for understanding problems when we just walk into them, right? It's in real life never the case that somebody tells you, go off and analyze this by doing this particular procedure, right? Instead, it's, can you figure out how much heat is going to be transferred here? And it's up to you then to go, okay, well, which of these resistances involved in this problem are big, which are small, which are important, which aren't important, right? And this is really our fundamental tool for understanding heat transfer problems. But it's really nice to have this tool, right? Because now I can take a situation like this where I have a bunch of things going on, right? I have convection, I have conduction through this material, I have some contact resistance, I have some conduction through this material, I have some more convection. For now, at least we're ignoring radiation. I got a bunch of different things going on, but using these resistances, I can represent all these different phenomena in one convenient network that I could look at, right? So, here, if I start over here at the warm fluid, I'm going to have a resistance to convection, resistance to conduction, a resistance to contact, and a resistance to conduction, and another resistance to convection. So my thermal resistance network looks like this, right? It's 1, 2, 3, 4, 5 resistances in series. And actually, what's even more important is I can estimate the value of each of these guys. And based on that, I can tell you what's important and what's not, right? In this particular situation, the heat transfer has to go through all these resistors. They're in series, and therefore the only resistance that really matters are the big ones. The small ones don't really matter very much at all, right? I'm going to get a temperature change across each of these resistances that is associated with how big the resistance actually is, right? It's the same heat transfer through all of them. So this temperature change will be the heat transfer rate times the resistance. So here, apparently, this convection resistance is much bigger than the resistance to conduction through here. So I'd expect a pretty big temperature change between the fluid and this surface, but not much of a temperature change across this material. And then this contact resistance is even smaller. It's basically negligible. I could just forget it if I wanted to. This resistance due to conduction through material B, though, is pretty big, right? So it's on the same order as the convection. I'll get a pretty big temperature drop here, and then this convection resistance is small, so it's not very important. If I were to look at the temperature distribution, it might look something like this, right? I'm getting a big temperature drop here, not much of one here, nothing here at the contact, a big temperature drop here, and then nothing over here due to convection, right? So in terms of what's actually controlling the heat transfer rate between these two fluids, the main thing I got to worry about is what? This convection resistance and this conduction resistance. This convection resistance and this conduction resistance. Everything else really isn't that important to this problem. If I could start adding things like radiation, so maybe I want to know, is radiation from this surface important? So how would I deal with that? Well, radiation would be in parallel with convection, right? Because the heat transfer from this surface can either occur by radiation or convection. It's not in series, it's in parallel. So I would add right here a thermal resistance in parallel. And now I could look at the value of that radiation resistance and compare it to the value of this convection resistance. In series, it's the big resistance that matters, right? In series, the energy has to go through all these resistors, so whichever one is big is going to give me the biggest temperature drop, and you see that here. In parallel, if I had a resistance in parallel here, it's actually the small resistance that matters because the energy gets to choose, and it's always going to take the smallest resistance path, right? So in series, the small resistance matters. So if I calculated a radiation resistance and I found that it was 10 Kelvin per watt, that's pretty big compared to 0.1 Kelvin per watt. That radiation really isn't important. If I calculated a radiation resistance and I found it was small relative to this, well, yeah, then all the energy is going through here, and all of a sudden this convection resistance isn't important anymore, right? So this is the kind of, not game, but this is the process by which we understand what's important and what's not in a heat transfer problem. So next time what we'll do is actually do a problem using thermal resistances, right? And we'll try to understand, based on those thermal resistances, what's important to the situation, what's not, and then also maybe try to understand what are some of the limitations of this approach, right? What thermal resistances can get us far, but they can only get us so far, and we have to understand where they kind of break down.